Hello everyone, we meet again. In this video, I will be explaining to you, discussing a bit of area of integration in the chapter of integration of part of calculus. So this is part of the applications of integration, where we're talking about how do we find the area of a plane bounded by certain boundaries or limits, and in particular, we can also name it as area of integration in general. So the prerequisite concept for this topic is the definite integral. So it's something that we've seen a lot. For example, like the integration of 1 until 2, let's say x squared dx, or let's say -4 to 3, 1/3 x plus 1, something like this. So anything with the limits. So when it comes to the area of integration, so the concept that we need to pay attention to is this. So let me just copy this very quickly for you. Whenever we have a function, let's say name it fx, then we can find the limit, the interval of x from a to b, and then you can see that there is a area in between here, the value, or the one with the green color. So we can always say this, the shaded area, the green one, as the limit of a to b integration fx of dx, but given that the fx must be at least 0, or it's a non-negative thing. Okay, so let me explain to you how it works, like what it means when it comes to area of integration. So the idea of area of integration, like for example, I'll just give you a simple one. Let's say I have x squared function, so we know it looks like this, and then let's just say this is 0 until 3, for example. And then what we want to find is, let's say, the area bounded this. Okay, so how this function works is that the procedure that I always keep in mind is that I have to find 1 as the boundaries. And then what I mean by the boundaries is what we call as the top and bottom. In this case, who is the top of the function or the boundaries? So it means is this one. I'll put it as the black one. You see, right? Who is the top? That's the function. The y equals x squared. And then who is at the bottom? In this case, I'll put it as the green one of the boundary. The bottom is in this case, this is the x-axis. Or that means the bottom is y equals 0, right? It's an x-axis. And then, so we finish with the boundaries of the top and bottom, and then we can decide who is the left and the right limits, or who are the left and the right limits. So in this case, we can check the limit from the interval from 0 all the way until 3. It means the left limit is x equals 0, and then the right limit is x equals 3. Then the third step that we can do is that now we basically set up the definite integral. Definite integral. So whenever we set up the definite integral, so for example, in this case, that I will put it as the integration of 0 to 3, so that's the left and the right limit, of the top, or I'll just put it this way then. So the left limit, this is the right limit, so this is usually I put it at the top minus bottom. Then in this case I put it as dx, and in the later discussion we can have the dy as well. So in this case of example, then we have 0 up to 3 of the top function, which is the x squared, so we ignore the y, and then subtracted by the bottom, which is y equals 0, so we put it as 0 dx, and then it means it's simply this, which is the same idea with the concept mainly that I put it there. Then of course then you just need to simplify, calculate this, put it in the integration, apply the definite integral, basically, right? Then there you go. So it's a 9 square units. So this is practically the procedure of how to calculate area using definite integration. So the key concepts is that about the boundaries, the limits, and then you set up the definite integral, then you calculate and evaluate over here, right? So the key will be there about the top bottom. So let us discuss a couple of examples. So example number 1. So I'll just take 3 different functions Technically, they're pretty much similar, but just give a bit of variation in each of them. So in this case of this, for example, we are looking for this part as the area that we're looking for. The function that we're talking about is the same thing. So I will not be discussing about like how we do the definite integration, like how do we calculate it. So let's just say that the function is y equals x cubed, and then minus 2x, okay, and then this is plus 2, for example. So in this case, how do we set up? As before, that means it's a function of, see the limits, the boundaries, right, from 0 up to 2, the left and right, and then who is the upper or the bottom, who is the top? And you see the top is the function, which is the x cubed minus 2x plus 2 dx, but then there's also the bottom, right, which is the y-axis, the x-axis, which is 0, so minus 0, then the x, then the rest is just calculate. So that whenever you calculate, you go back to that idea of definite integration. That's why definite integration is the prerequisite for this particular topic. Let's say an example 2. In example 2, let's say we have, the name is, basically it's very much similar. Let's say the name is this, right? And then, so we have, the interesting part here, we have like 2 shaded area, like the first one and then the second one. So as we're talking about area, we have to talk about positive values, right? And in this case of this, we have to separate the two, area 1 and then area 2. Then after we find each of them, then we add up the two to we get the final result. So in the area number 1 over here, so same thing. So we have the 0 and then we have the unknown number. Here we have the 2, right? So first thing first, then we need to find who is this missing number, right? And then this is the x-intercept, and then we know that x-intercept comes when y equals 0. So here we are, x squared minus 2 equals 0. So we have x equals 0, x squared equals 2, so the x is plus minus square root of 2. So here this is negative root 2, this is square root of 2, and that's it. So then whenever we set up the area number 1, it means from 0 all the way root 2, and then see who is the top and then who is at the bottom, right? So who is the top, who is the bottom? The top is the x-axis now, which is 0, subtracted by the function x cubed minus 2x. Then you do the calculation. But for the second area, the top is, now it's the curve. Interestingly, so they change. And then the bottom is the x-axis, which means we can set up from root 2 to 2. Now it's the function x cubed minus 2x. So we subtract by 0. So then you will see why it matters, and then we can't just swap it however we like. So further detail of that, you can read through the handout that I shared with you. Just everything, the detail is over there. Last but not least, the example number 3. So now everything there is beneath the x-axis, below the x-axis. So how do we find this, or how do we set up the definite integral? So the area will be from 0, see, right, the left limit, and then the right limit here, 2. But then who's the top, who's the bottom? See, the top is, again, the x-axis, and then who is the bottom? It's the function. So in this case, the function is y equals x cubed minus 2x and then minus 4. So here we have the top, just 0, minus the function. Then it's a matter of calculation. So that's it, basically. So whenever you see this, then it's always go back to the main concept, or the main procedure is like top, bottom, left, right limits, and then set up the definite integration. Then we do the evaluation. But when it comes to, we're talking about the why it works, like how it works, so we can go back to the reverse video that you were exposed from Professor Dave last time, right, in the YouTube. So you can go back to the idea of that whenever you have a given area like this. Let's say I'm just using this one. So you can always go back to the principle of making like very small rectangles, which then later we call it as Riemann integral. So it's like approximation of small rectangles, but added up, so then we cover up all the area. So with this being said, thank you for listening, so then watching as well. Hopefully this helps. Then if you found any problem or question, of course feel free to ask. Thank you.